Rohit, you want to play with the lights? Thanks. Oh, okay. So let's begin today. This is lecture 11. For those of you who are on time, what you may not consider a treat, I'm going to show you pictures of some of the names we've been playing with. Okay? Here's Lobatel. 1661 born. It's been around a while. You notice all of these people have curly hair. It was a style. De Moivre, he was one of the guys who started talking about probability theory and relative frequency. Here's Laplace. Handsome young man, no curls. French, by the way. French. Gauss, the famous Gauss. I mean, there was such a person. I want you to understand it. These were human beings who did some work, studied, and produced great results. German. Poisson. We should all bow down to Poisson. French again. Chebyshev. Russian. The Russians were a big deal in this period also. Why do I mention his name? Anybody remember? No, that's Chapman. Kolmogorov. What's that? Little Women? Yes and no, but there's a name. It's called Chebyshev's Inequality. And remember, I told you that you can spell his name any way you like. That's one way. You could put a TCH, whatever you want. Boucher, you're going to hear about him either today or on Wednesday. You'll be sorry to hear his name. Yes? Oh, we lost that again. Sure. Okay. Okay. Boucher, French. Markov. I mean, it's good to see what these people were really alive and what they look like. And you have to understand, you know, they were not geniuses from another space. They were like you. You know, they took a problem and they solved it. Erlang, father of queuing theory, Danish. Chapman, as in Chapman Kolmogorov, British. Polacek, you haven't seen his work yet, Austrian, you'll see him later. Kinchin, Polacek and Kinchin have a name together, you'll see that later. Chapman Kolmogorov, another Russian. He was a mean guy, by the way. Kendall, you haven't seen his name, you'll see when we get to MG1, British. Chernoff, an American. Chernoff Pound. Takacs, you haven't seen him, the mad Hungarian, brilliant theorist, wrote a great book on queuing theory. But these are not all the people I could have shown you, but you've seen these names. Jackson, you're going to see later, an American. He actually was a faculty member here at UCLA. And a key paper he wrote, a brilliant paper, I'll take it, there's something marvelous about it. I used his results in my own dissertation. John Little's result, American. Kingman you haven't seen yet. Deep mathematician. He talked a lot about GG1. Okay, just thought I'd entertain you a little bit with this. We can look at this again if you like at some point. Maybe you don't. Okay. Okay, so for today I want to start off as always with a quick review. We're talking about Markovian Qs in equilibrium, and in particular well actually let me go back a little bit. Prior to last lecture we have the famous equation 19 that you like, or yeah, you like, right? Okay. What's your name? Matt. Okay. Matt's equation. Okay. And the most general case we used that equation for was this one. This has everything, soup to nuts. It's multiple exponential interarrival times, exponential service times, multiple servers, finite storage, finite population. That's listed here. And this is the state diagram. The result is right here. And I pointed out that P0 is complicated. But you can play with little m, capital K, and capital M to generate all the other examples we had. You can go to MM1, MMM, MM1K, etc. Then we moved into chapter 4. We just started that last time a bit. And I pointed out we're going not to birth-death systems, namely more than just nearest neighbors. So we're moving into this region here that I've circled in red. It's random walkers here, but in particular we're going to Markovian. So we're in this space here. And what's characteristic about that space? You can go from any state to any other state, but the underlying distributions are memoryless. That's why it's on the Markovian. The new thing is you can go from any state to any other state. Instead of the birth-death process, which we had earlier, we only go to neighboring states, up one or down one. So that's brought us, and the problem is that equation 19, Matt loses here. It doesn't work anymore, except in those cases that drop to a birth-death process. So we're basically going to more than nearest neighbors. If we went most general, we can't handle it. It's just too complex. But some of these cases have some useful structure, which we're going to see, which allow us to make some results. And since we can't use equation 19, we're back to what John told us the other day. We're going to use the inspection method, okay? The inspection method. Namely, we're going to use this idea of pi q equals 0. Remember, in discrete time, we had pi equals pi p. In continuous time, it's pi q equals 0. We're dealing with probability rates instead of probabilities themselves. And when we go to queuing systems, we change notation for pi, and we call it p, something we've been using before. So it's the vector little p we want. We solve it by pq equals 0, by inspection, by balancing flow. Again, flow in equals flow out. And of course, we'll always need this conservation of probability equation. So again, the general approach is, for all of these now, will be flow in equals flow out in equilibrium. And as John says, you can write the equations down by inspection. And the trick is to solve the equations. You can write them down easily. But how do you solve them? Birth, death, equation 19. Others, you try to do a z-transform or some other method that you like. But we're going to find some that we can handle. And meanwhile, what we did as well is I asked the question, is the probability of finding k in the system the same as the probability that an arrival finds k in the system? And we proved that, yes, that's true, even as a function of time, not only the equilibrium but the transient results, if it's Poisson arrivals. So Poisson arrivals take a random look at the system. So in general, pk of t equals rk of t. Very valuable. Okay, so let's move on today now to some interesting cases. I want to introduce something called the method of stages. And basically, we're going to exploit the simplicity of exponentials. And the simplicity is that they're memoryless. So we did so well with the exponentials earlier. And we're going to use the power of the exponentials to solve some queuing systems in particular. Now, L11, bless his heart, recognized that the memoryless property was very valuable. And he wanted to go beyond pure exponential and still use the beauty of the memoryless property. So he cooked up this thing called the method of stages. This is way before the mathematicians jumped in, and was able to use it to generate some cases we can solve and which generalize some of the distributions. Okay. So basically, he formed a collection, a particular collection of exponentials. And again, this is due to L11. So let's consider some things. Let me start with a single server, say at a rate mu. Here it is. And eventually you come into service and you leave service. And if that's the service time distribution for some queuing system, then we denote the service time density by B of x. In this case, what is it? It's mu e to the minus mu x. This only for x greater than or equal to 0. And we call this a service facility. Nothing new here. That's what the MM1 system used, MMM used it, a bunch of these, etc. Now, in this case, what's the average service time, x bar, in terms of mu? Anybody remember? What's the mean of an exponential? 1 over the parameter, so 1 over mu, right? And we've calculated the variance of that. We used b to remind ourselves it's the variance of the service time. And for the exponential, what was that? It's 1 over mu squared. And again, B stands for service. Why? Because A stands for arrival, and B follows A. It's just, you got to make some definitions. Okay. Now, let's consider something else. Let's now consider something at the rate 2 mu. And I want to consider two of them as service facilities. So what I'm going to do is I'm going to surround this thing with a red circle, and the red circle is the service facility. And what is it? It's a system, this red circle. A customer comes in, and the first thing the customer does is go through an exponential service time at a rate 2 mu. But he can't leave, he's not finished with the red box. Once he goes through that, he has to go into another box of the same rate, spend an exponential amount of service time there, and finally that customer leaves. So there are two stages here, stage 1 and stage 2. And I'm going to denote the density of the time that you spend in one of those boxes. I'm going to call it h of y. So the density for each of these boxes we call h of y. And can someone tell me what h of y is? What is that density in each of those little black boxes? Look up here. That's the exponential surface time density. The only difference, I got 2 mu, right? So the h of y is 2 mu e to the minus 2 mu y. This is called a two-stage Erlangian. Two-stage Erlangian surface facility. And it's denoted as E for Erlang, 2 for the number of stages. Well, while we're at it, let's calculate the mean time in any one of those boxes. What's the average value of y? Come on. Excuse me? 1 over 2 mu, right. 1 over the parameter. And what's the variance of y? I'll call it of h, so that since I used h as the density name. Yes. Exactly. 1 over that quantity, 2 mu squared. Right. Okay. And those times in each of these black boxes is independent. So when you come into the red box, you get stuck in this exponential surface time. Then you go to another one, and then you leave, and the time in each is independent. Okay. And only one customer at a time in the red box. So you can't have both of these little black boxes being used at the same time. You come in, you go to 1, you go to 2, you leave, then the next guy can come in, if there's another guy to come in. Okay. So the service time is the sum of 2 exponentials, right? Something we're very familiar with. 2 independent exponentials. So b of x, the time in the box, b of x is the time in the whole box. I'll write that in red, which is what we're trying to cook up. What is that in terms of functions I just wrote down? If I add together 2 independent random variables, what's the density of the sum? Convolution of the individuals, right? And what is the individual? H of y. So it's h of x, I'll use x now, convolved with h of x. Let's look at the transform of the overall density. What is that equal to? It's equal to the product of the transform of each of the h's. And I'll denote that by h star of s times h star of s, where I'm saying that h of y has, as its Laplace transform, h star of s. Of course, b star, we remember what that is. That's the Laplace transform of b of x. E to the minus sx dx over the range 0 to infinity. H star of s, same thing, it's a definition for h of y, integral 0 to infinity h of y e to the minus sy dy. Now, can you tell me what is h star of s? You knew that for the exam. What is the Laplace transform of an exponential density? The clock is ticking, the exam is running, and you're getting worried. Excuse me, what is it? 1 over? You forgot this little guy here. E to the minus thing y has to transform 1 over s plus thing. But I multiplied by thing. So it's thing over s plus thing. Right? Okay. So this is, now tell me what I'm trying to write down here, opposite this equal sign. 2 mu s plus 2 mu. Okay. That means that b star of s is equal to, we know it's h star of s squared, so it's this baby, 2 mu over s plus 2 mu quantity squared. Now let's invert it. To get b of x. Okay? Well, you've seen this before, and it's one of those entries in your table, which is not that easy to remember because we're going to go beyond just 2 of these guys. So let me remind you, it's table I4 number 10. Entry number 10. And that says the following, that 1 over s plus a to the n plus 1 power has, in time domain, a function f sub x of x, which is equal to t to the n over n factorial e to the minus at, and I should have used a t instead of an x here as the variable, so let me do that right now. Okay. That you probably don't memorize, you can look it up. That means we got, in this case, n is equal to how much when I want to transform it? If I want to transform this baby, what's the n I'm going to use in this equation? 1. Because this, notice, is n plus 1. And right now it's a square, okay? So let's write that down. That means 2 mu over s plus 2 mu quantity squared has as an inverse what I'll call b of x now, and that's equal to 2 mu quantity squared, because that was there, that's not in the table, I have that as an extra, over n factorial. What's n? 1, so it's 1 factorial, which is 1. And then I get t, well in this case x, to what power? N, which is 1. And then e to the minus 2 mu x. Okay, so that's what it looks like. So I'll just write it out. The thing I just drew on the previous page says b of x has a density which is 2 mu. I'm going to write it this way, times 2 mu x e to the minus 2 mu x. And that's for x greater than or equal to 0. And let's circle that because it's important. That's the two-stage Erlangian. So notice what's happened. In the red box, I've got a service time density, which is not an exponential. It's related to it, but it's not an exponential. But it's made up of 2 exponentials, which suggests maybe there's a way to keep the memberless property and account for it properly and get a new service time density. Suppose the service time density was not an exponential, but it was this baby. Well, Erlangen is suggesting a way to cook that thing up and hopefully keep the exponential properties as in this box. And he's going to generalize that, of course. But meanwhile, let's find the mean and variance. Now, you can do it in three ways. Way number one is from the figure. The things are independent, the variances add, the means add, etc. Second way is from the moment generative properties of B star of X, or B star of S. Properties of B star of S. And the third way is a direct calculation from the red equation. Okay. Well, let's do it from the figure. It's the easiest one to do. So, you tell me, what is X bar? Let's look at the figure. What is the mean time in the red box? Yes. How'd you get that? You're correct. Yeah, 1 over 2 mu plus 1 over 2 mu, time in each of these independent stages. In fact, it doesn't have to be independent. Expectation of a sum is the sum of the expectations. So that's equal to twice 1 over 2 mu, which is 1 over mu. And notice, it's the same as the original service time. The one I've kept both of these boxes, the pure mu and the red box, they have the same mean. And that was on purpose. I'm trying to keep things consistent there. So that's good. Okay, let me just say, same as a one stage. Okay. Now, since the random variables in each box are independent, then the variance is add, right? So the variance of the big box is equal to what? It's the variance of H plus the variance of H. And we just figured out what the variance of H was, is 1 over 2 mu squared, right? So it's 1 over 2 mu squared quantity plus 1 over 2 mu squared. And that's equal to 1 over 2 quantity mu squared. Namely, it's half of one stage. Let me write that a little more carefully. It's a little sloppy here. That's 1 over 2 mu squared. 1 over mu squared is a variance of a single stage. Half of that is a variance of a two-stage. So something interesting is happening. I've kept the mean the same, but I've dropped the variance, which is, you're going to see, is very nice. Okay? Now the question is, what is the state of the system? What's the state variable? Suppose I had an M E2 1 system. Okay? What is the state variable that I need? In other words, what do I have to tell you? So I've given you all the information you need in order to predict the future as any other information could give you. Okay? So I'll draw the picture. It looks like these two service inside the big red baby. and I've got a queue here in front of it. And arrivals are coming in at exponential rate lambda. They go into service. They go hopping through this two-stage system, and they leave. And each of these is at a rate 2 mu. So the system's running. So there may be some people in the queue, obviously. What is a natural state variable? What do you need to know to capture everything of the past that you need to know? Right now, the system's running. It's got people in it. What do you want to know? Yes? You raise your hand? Scratch your head. Okay. Scratch your chin. Come on, somebody. Excuse me? You've been reading the book. You want to know which stage the customer is in, right? If there's somebody in service, okay? So you need the stage of service. And you only need the stage because how long the person has been in that stage doesn't matter. Why? It's exponential. But if it's in stage 1 or 2, it does matter. If he's in stage 2, he has no more to go. Just finish the one he's in. Stage 1, he's got to finish 1, and then go into 2. So I got to know which stage is it. What else do I need to know? Suppose it was MM1. What do you need to know? Yes. That's given. Lambda and mu is given. That's an input. This thing is dynamic. People are coming in, going out, etc. If it was MM1, what is the state variable? What do you remember? P sub k? What was k? What did it represent? Not quite. People in system. Well, don't I need to know the number in system here? I need to know the number in Q here, right? Or number in system. Either way, the same information. So I need to know, if you will, the, I'll call it number in Q. If I know that, I've captured it. What else could you tell me about the past that could affect the future? Nothing. Each of these guys in service is going to spend 2 stages of service before they get done. So what this means is I've basically got a 2-dimensional state space. We haven't seen those before. Okay? I could draw it right here. I could draw the state space as 2-dimensional. Let's call this the, say, number in system. And this is the stage of service. And each of these boxes I'm drawing here is a state. It's 2-dimensional. And let's label it. 0, 1, 2, 3, stage 1, stage 2. Now, if I'm in the system, for example, can I exist in this state? The little one I marked red. Can there be a guy in stage 1 of service, but nobody in the system? No. So that red state doesn't exist. Can I be in the 1-1 state? Yes. What is it? There's one guy in the system, the queue is empty, and the guy in service is in this state right here. Or I could be down here. Okay, one guy in the system, but he's in this state of service. Okay? Could I be in stage 2 and nobody in the system? No. So in some sense, these are not allowed. Okay? But what are the so these are states. Now you move among states. Can I move from, let me use another color now. Can I move from this state to this state? Gets tricky. Think about it. You got a guy in this stage of service. Next state, nobody's in the system. Can't happen, right? Can I move from this state? One guy in system is in stage 2. If he leaves, where do I go? To a state I haven't showed you. Totally empty system. I tricked you, right? There's another state which is totally empty. But look, it's getting complicated. You're going to jump around among all these states. Two-dimensional, multi-dimensional state spaces are more complicated. And in fact, if I had more stages, I'd have multiple rows, and I could go all the way to infinity to the right. Pain in the neck. Now, you said something before which solves this problem, okay? What did you say, and what do you think you solved? I think because you understood it. Okay. You're saying the state I want, a one-dimensional state, would be the number of stages left in the system. Tell me why that works, because it does. And that's one-dimensional, notice. Each guy in the queue counts for how many stages of service? 2. Each guy in the queue is going to go through 2 stages before he gets out of there. So each of these guys in the queue counts for 2, and the guy in service depends. He either is in state 1, in which case he counts for 2, or in stage 2, he counts for 1. But that captures the exact situation I want. So suddenly it's a one-dimensional state description. Fantastic. Now it's easier to solve. So let's keep that in mind. We're going to use that as we go on. Okay. Before we go and take advantage of that, let's do the next obvious generalization. Now I'm going to go, instead of just 2 stages, say R stages. So let's write that down. I got a bunch of stages, R of them, each at the rate R mu. And we're going to go between them. And I'll draw the Q back here. And I'll draw my fancy red circle around the whole shebang. Okay. What I've drawn here is an R stage Erlangian service distribution. R stage Erlangian. And that's denoted, no surprises, E sub R. And let me number these things so you see it exactly. This is 1, 2, up to R. And each of them is an H of Y. Each of them has a density which is exponential. R stage Erlangian service distribution. Coming at a rate lambda, go through the Q and go through R stages of service. Okay, so let's now find out what is H of Y. Anybody? What's the density for each stage? It's an exponential. The parameter is R mu. So it's R mu e to the minus R mu y. total time, I need a different variable here, let's see. No, let's leave this. Let's find the expected value of the time in a stage. That's 1 over r mu. Okay? Expected time for x, namely x bar, is equal to r of those. So it's r times 1 over r mu. I'm adding them together. And that's now 1 over mu. Once again, it's the same as a single stage on purpose. Let's look at the variance. The variance of the overall distribution is equal to r of these individual variances, which is 1 over r mu quantity squared. So that's equal to 1 over r mu squared. So it's dropping again. It's dropping by a factor of r. Mean is constant, dropping by a factor of r. And while we're at it, let's do the coefficient of variation we talked about one time before. We define that to be the standard deviation over the mean. In that case, I'm going to get just 1 over the square root of r times 1 over mu over 1 over mu. So it's equal to 1 over the square root of r. Notice that the coefficient of variation is dropping. Okay? And while we're at it, let's cook up a few more simple things. B star of s is a bunch of h's of s multiplied together. There's r of them. So, and each h has a transform which is r mu over s plus r mu, just like before, but to the rth power. And if you consult that table, I gave you the expression for it up here, number 10. It's right here. But now n is r minus 1. I'll write it down what it is. It's equal to r mu. I'm going to pull one of those out times r mu x to the r minus 1 over r minus 1 factorial e to the minus r mu x. Again, x greater than or equal to 0. And this is the airline distribution. I'll put E sub r over here. I gave it a name on top of the page. This is its density. Okay, now let's see what that looks like. And no surprise, I happen to have saved it. It's right here. I'm going to pull it into the material here. There it is. This is the service time density. Whoops, let me write that. I'll write it larger. B of x versus x for the Lagrangian distribution E sub r. And notice here, when r is 1, it's a plain old exponential. That's this curve here. And when r is 2, it looks like this. It starts off at 0 and climbs. And we've seen this before. You notice the mean is fixed. So the mean is this thing stays right here. Every one of those curves has a mean here. But the standard deviation shrinks. And the central limit theorem says, as I add together a whole bunch of independent random variables, in this picture there's r of them, as you add together a large number of independent random variables, the density of that sum begins to go Gaussian. And you can see that here. I said it in red. This curve, when I've added together 20 of them, begins to look like that. We saw that before. I warned you. I showed you this one time before. And then the limit, as r goes to infinity, the variance goes to 0. the mean stays fixed, the total area is always 1, that's called the unit impulse at 1 over mu. And it's a unit impulse at the point x equals 1 over mu. So this red arrow is the notation for unit impulse. It has area 1, infinite height, sitting right at 1 over mu. Okay. Now, I just said that. Let's prove some of it. But any questions about this picture? It's a very nice family. That's what Erlang is cooked up. He's going to show you how to take any one of these densities and find the behavior of a queuing system where that's the service time and the arrival time is Poisson, exponential, at a rate lambda. So a huge generalization, a whole family of new service time densities, not only the exponential, but this whole family of Erlang. But the family has a particular property. It's got smaller and smaller variance than the exponential. You can sort of model any system with a variance less than the exponential with the Erlang gear. Okay. Let's find the peak. Of these functions, of each of these black functions. Okay? How are you going to find the peak? Well, differentiate b of x dx and set it equal to 0. So you're going to differentiate this expression I have up here. Let's put that in red for the fun of it. If I differentiate that, I got two functions of x. The one in the numerator and the eta minus r mu x, so I'm going to get two terms. The differential of a product is the product of each, holding the other one constant. So we get when I differentiate the first thing, the r mu x to the r minus 1, I'm going to basically get an r mu. I'm going to pull two of these out, and I'm left with r minus 1, that was the exponent, times the same thing to 1 power less, r mu x to the r minus 2. And don't forget the exponential e to the minus r mu x. And downstairs, I simply get that factorial which is there. And then I get a negative, because I'm going to get a negative when I differentiate the exponential, which I haven't done yet. I started with an r mu x to the r minus 1. Get to e to the minus r mu x. And then got an r mu squared when I do the differentiation over the r minus 1 factorial. Now, if I want to set this thing equal to 0, what does it is that r minus 1 is equal to r mu x. So x at the peak, the value of the input variable x at the peak is simply equal to r minus 1 over r times 1 over mu, which as r goes to infinity goes to 1 over mu. So the peak is moving from the left at 0 for r equals 1 and moving right over at this rate, a very simple rate, and eventually landing up at 1 over mu. So what we said about where the peaks are is correct. Let's look at the limiting distribution now. As r goes to infinity. Well, let's look at the Laplace transform of this guy. B star of s, we already know, is simply a power of r mu over s plus r mu, all of that to the rth power. And if I want the limit of that as r goes to infinity, well, what is the limit of that function? That's equal to the limit as r goes to infinity of, let's divide by r mu. I'm going to get a 1 over 1 plus s over r mu, all of that to the rth power. But we know something from high school. We know that e to the x is equal to the limit as n goes to 0 of 1 plus x over n to the nth power. So the limit of b star of s is equal to, I'm just going to turn this thing upside down, limit as r goes to infinity of the quantity 1 plus s over r mu to the minus r. So what is that limit if I know this expression up here? It's e to the minus s over mu. And now if you go to table I4 and you look at entry number 3, you'll find the following entry, that e to the minus s over mu is a unit impulse, u sub 0, at x minus the shift 1 minus mu, 1 over mu. Namely, it's a unit impulse. So this is one way to show analytically that you end up with an impulse. Okay, so we have a means here for approximating any distribution with a mean value, say 1 over mu, and a variance 1 over r mu squared with this Erlangian stage device. And we're going to find out how to solve that. So we're going to end up, next we're going to solve. Let's try to solve m e sub r 1. That's the next job. Okay, let's take a break. Okay, let's get started again. John, you had a question?
Yes, previously you showed us a similar Gauss diagram with the Poisson process.
Yes.
It was also going like Gaussian and impulse, but what's the difference between the Poisson and Erlangen distribution?
Well, with the Poisson distribution, it's hard to take advantage of the exponential behavior as we have now. It's a very similar distribution, but now that we know where it comes from, we can now take advantage of this structure, and in particular talk about the state diagram we need. If you recall, I guess I was doing it up here. Yeah, we're going to have a state diagram which is not requiring multi-dimensions again. So this structure leads to a very similar density. In fact, I called it the Erlang when we looked at the Poisson. But given this structure, we could take advantage of that, create a single state variable, and get a very nice way to get the solution. You're right, they're very similar. Okay. So we're going to solve MER1. Let's draw the picture. We have a queue. We have R stages of service. Let me identify them now as 1, 2, state I, and finally state R. Stage, not state, stage. And please don't confuse those words. Okay, so we have a system like this. We have a queue, and we have a service facility. Consisting of R stages of Erlang, of exponential. People arrive here in the usual way. They work their way through, and they finally leave. Now, the state variable we agreed need only be the number of stages left to be done for the customers in the system. So let's define that right now. Let J equal the number of stages left in the total system. Number of stages of service. And suppose the system has K customers in it. Customers, not stages, but customers. And suppose the customer in service is in a particular service stage. Let's call it the ith stage. He's in the ith stage of service. What does that mean? I'll use a blue color. That means there's K minus 1 in the queue, and there's 1 in service, and he's right there in the ith stage, as I've shown in blue. So I can write down that for this situation, J, the number of stages of service, well, there's K minus 1 in the queue, And each one of them is going to count for R stages of service. Plus, the guy in service has so many left to go, basically. R minus 1, R minus I, plus the stage he's in. The stage he's in doesn't count as being done. He's still in there. And how long he's in there doesn't matter because it's exponential. It's memoryless. This is for k greater than or equal to 1. And 1 less than or equal to I, less than or equal to R. So that simply gives me Rk minus I plus 1. So I've mapped from a two-state, two-dimensional system, number of customers and stage of service, to one which is only the number of stages left in the system to be done. Okay. And now I'm going to define capital P sub j to be the probability there are j stages left in the system. And I want to find capital Pj, because once I get that, I'll be able to say a lot of things like how many customers are in the system, etc. And eventually find the response times, etc. So let's do that. Now what I've just shown you is for j equals 0, 1, 2, etc. But P sub I, excuse me, P sub 0, no stages, is included there. What I wanted to actually say here is that P sub I is 0 for j less than 0. Okay. Now, eventually, if I find capital Pj, what I really want is little p sub k, our old friend, probability of k customers in the system. And what is that? That's a sum of, over a certain number of stages, it's a sum over a certain number of j's, j going from k minus 1r plus 1. Can someone tell me what's going on at that lower limit, where customers are? There's k minus 1 in the queue, and one guy in service, and he's in the last stage, because he only counts for one more. And that goes all the way up to kr. Again, there's k minus 1 customers in the queue, and one customer in service, adding up to k totally, and that customer is in the first stage of service. He's accomplished no service stages yet. So this is the way I'm going to get this. All it's on the PJs, okay? And this is k equals 1, 2, etc. So in our usual way, let's draw the state diagram. Why? Because I want to use the inspection method by balancing flow. So let's draw it. This is state 0. State again is j, number of stages of service. 1, 2, up to r plus 1, then on up to j minus r, to j plus 1, etc. I left out j here. Let me do that. And there's dots all over the place. And the transitions are what? What are they going to look like? This is a little bit like that midterm problem, if there's nobody in the system, namely no stages of service in the system, which is also no body in the system, what's the only thing that can happen? Nobody can leave. There's nobody left to leave. So all we can do is have an arrival. So somebody comes in. What happens to this diagram, which is the diagram for stages of service? Where do we go? R. R is now, you thought it was 2, right? Jumps all the way up to R at a rate lambda. And similarly from stage 1, I'm going to go to R plus 1 stages with an arrival. Of course, any time I'm in a state, say state 1, how can I leave that state? Besides an arrival, how can I leave state 1? What does state 1 mean? One guy in the system, and where is he? Last stage of service. All he can do is finish that stage and go away. When he does that, what state do I move to? 0, right. And at what rate does that happen? RMU. Because every stage is operating at state RMU. Okay. And similarly, I can enter state 1 from 2 at a rate RMU. And from state R, I can jump up where? To R plus R. So just jump up there. And I jump down. And from R plus 1, I come in at a rate RMU to R. State J minus R jumps up at a rate lambda to state J, namely adding R more stages of service. From state J, I can go down at a rate RMU, and I can enter it from J plus 1 at a rate RMU. And from J, I also jump up to J plus R at a rate lambda. So this is the state diagram for number of stages in MER1. And by stage, I mean stages of service. Okay? Next step. Inspection method, which means draw circles on important states and make sure flow in equals flow out. He's taking over for you. What? All right. Easy come, easy go, huh? Okay. So which states do I have? Well, clearly state 0 is a special state, so let's balance its flow. That says that the rate out, lambda P0 equals R mu P1. Now I'm going to make the following assumption. I'm going to say, I'll mark this in red up here, that P sub J minus R, capital P sub J minus R, for J less than R is equal to 0. Namely, for J minus R less than 0. Because I want to simplify things. I want to make believe there are negative states, but they don't count because they count for 0. So I can write the next equation for all J. This one I just wrote down was for J equals basically 0. Now I want this for J equals 1, 2, etc. Just a simplification. I've not shown you before, but it's handy. So it'll work in an intermediate state. If any state, I can leave it with lambda plus R mu Pj. I enter it from below at a rate lambda Pj minus R. And here's where I'm taking advantage of those zeros for negative values of the subscript, or enter it from the one above at a rate r mu, p sub j plus 1. So I've taken a very simple function in red here to allow me to write this down without worrying about states 1, 2, etc. being different. Because there's sort of, in some sense, phantom states that are coming into these guys, but they have 0 to contribute. So it makes it handy. Okay? Next step. I've got that, now what? Quiz problem, homework problem. You said to draw a circle. What do I do next? Wrote the equations. After I got the equation, there they are. Now I want to solve them. Right, make them z. So multiply z to the r, sum with a range, and look for p of z. Okay? So let's do that. That's summation. I'm going to take the lambda plus r mu outside. It's a constant. Then I'm going to sum this thing. Now notice, j goes from 1 to infinity. So if I'm going to claim that's the summation from 0 to infinity of p j z to the j, I better give back what I took away, what I added in. And what did I add in? The 0th term, which is minus p0 z to the 0, which is 1. So far, so good. Now for the next one, when I multiply by z to the j, I really want to take away r of those, so I get a z to the j minus r. So let's take that outside along with the constant lambda, which is there. So let's get lambda z to the r. And then I get a sum from j equals 1 to infinity of p j minus r z to the j minus r. And then I got one more term to worry about. And that's pj plus 1. I'm going to multiply z to the j. Better add a z, take it away. So I got r mu over z times summation pj plus 1 z to the j plus 1. And that's from 1 to infinity. And I'll worry about accommodating for what I need to do there later. Okay. So let's take it down. I get lambda plus mu p of z minus p0 is equal to lambda z to the r. And what I've got now, if j starts off at 1 for an arbitrary of r, 1 or larger, it's all accounted for by either 0 or p0 or real p. So that's the full z. That's p of z. And then this other term, the r mu over z, I got to account for some missing terms. So I get p of z. And let's see, when j starts off with 1, I begin with p2, so I'm missing p0 and p1. I put it in for the p of z, give it back. So it's minus p0 minus p1z. Looks like I've been doing a midterm problem here, doesn't it? Okay. Okay, factor out the p of z and put it all on one side. So p of z equals the following lovely little equation. And I'm going to recognize I get a 1 minus z function here, so I'm going to get an r mu. I'm doing a little bit of calculation here. There's a 1 minus 1 over z times p0. Where did that come from? It came from this term here. The lambda mu is out. And from this term here. This one gave me the 1 over 1 minus z. The 1 over z term. Okay. Downstairs, I'm going to get the lambda. Oh, there was an r mu here. Nobody caught me. It's lambda plus r mu. So it's a lambda plus r mu minus lambda z to the r. That came from this first term on the right-hand side. And then I get a minus r mu over z That came from the other term. And I've already taken advantage of this first equation. I've already taken advantage of this and get it into the P1 term, which was right over here. You can do that for yourself. It's trivial, okay? Okay. So now let's multiply by minus z all over. And I get P of z equals the following. I'll get an R mu 1 minus z P0 downstairs I get a lambda plus R mu, get an R mu, sorry, an R mu plus lambda z to the R plus 1 minus lambda plus R mu z. And that's an intermediate step, but let's box it. Now I need another equation I haven't used. I use the circled equation here to get rid of the P2. What other equation do I need? Always? Yes? No? This? Yes. It's one or the other, right? Sum goes to 1, right. I need the summation. Whoops. I need the summation of P of 1. So capital P of 1 must equal 1. That works for stages or for number and system. And when you add them all up, all the probability goes to 1. And let's put z equal to 1. And what's going to happen now? Numerator goes to 0. When z goes to 1, denominator goes to 0. Son of a gun. In fact, you'll almost always, as I told you many times, get a factor 1 minus z downstairs. But I want to take this limit as z goes to 1. So let's write that down. Limit as z goes to 1 of this expression. Let me write it out again. Of R mu 1 minus z P0 over R mu plus lambda z to the R plus 1 minus lambda plus R mu z. So what am I going to do? I showed you his picture before. L'Hopital's rule, right? The guy with the curly hair. Okay. And what is the rule? It says the limit of something, if it doesn't exist, you can differentiate the numerator and differentiate the denominator independently and take the limit. Okay. So let's do that differentiation. So upstairs, when I still have to take the limit, so let me leave space to say that. Of differential denominator, different numerators. Different numerator gives me what? Gives me minus R mu P0. And downstairs, I'm going to get what? I'm going to get R plus 1 z lambda z to the R. And then the other term I get is just minus lambda plus R mu. And now I set z equal to 1, and I get the following. I get minus R mu P0. Z goes to 1, I get R plus 1 lambda minus lambda minus R mu. And that's equal to R mu P0, I'm going to multiply by minus 1, over R mu minus R lambda. And that's equal to mu p0 over mu minus lambda. That says that P0, and all of this equals 1, right? P0 is equal to 1 minus lambda over mu. And that's equal to P0 as well, little p0. When there's no stages, there's no body. And we know something. X bar equals 1 over mu, no matter how many stages there are. So basically, I got rho, which we know is lambda x bar, is equal to lambda over mu. So finally, we get that P0 is equal to 1 minus rho, which is also equal to little p0. And we'll be using that later. Let's box it. So let's put that into the P of z equation. And I get R mu, instead of P0, I'll put the 1 minus rho. And all of that was times 1 minus z. And downstairs, I'm going to get what I had before. It's going to be R mu plus lambda z to the R plus 1 minus lambda plus R mu z. Next step, what's the nature of this step? What do I want to do next? I got P of z. What do I do now? I want to invert it using partial fraction expansions. So let's invert P of z. Okay? Let's try this for MM1 just for the fun of it. But notice that when I invert this thing, I'm going to get the probability for number of stages, right? Let's do this for a moment for MM1 instead of MER1. Okay? In this case, R is equal to 1, so P of z is equal to mu 1 minus rho, 1 minus z, over mu plus lambda z squared, R is 1, minus lambda plus mu z. Well, you can see that the denominator has a root z equals 1, and that's easy to do this case. It's just a quadratic. So I get mu 1 minus rho, 1 minus z, and I'll get a 1 minus z times a 1 minus rho z. And the 1 minus z's cancel. And I've divided this by lambda actually already, by mu, so this term is gone. There's no mu here. And that's equal to 1 minus rho over 1 minus rho z. That should look a little familiar. But in case it doesn't, you can invert that by inspection. That's 1 minus rho to the j. But remember that pk equals pj equals little pj because there's only one stage of service. This is exactly equals mm1. And yes, it's consistent. So far, so good. But that was a little example. Okay? Now, this is going to get more complex, so we're going to take a bit of a dive into some calculations, which are not trivial to do, but illustrate an important point. Okay? But as you said, John, I want the partial fraction expansion, right? which means I've got to find the zeros of the denominator up here. What's one of the zeros? What's one root of the denominator? Z equals 1. We said that earlier. Okay, but there's many others. Okay? So we have to find, let's first find how many roots does the denominator have up on top of the page? It's r plus 1. Roots of the denominator, d of z. I'm going to write this thing as numerator of z over denominator of z. And the roots of the denominator now become the item of interest. So, one root at z equals 1. Okay? So we've got to find the rest. So let's right away write down d of z as follows, which was r mu, I'm going to write it out again, plus lambda z to the r plus 1 minus lambda plus r mu times z must be equal to 1 minus z, and what's left, if you divide it out, is r mu minus lambda times z plus z squared plus dot 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 out through z to the r. How do you find that? You take the d of z, divide by 1 minus z, do long division if you like. You keep adding the extra z, you got to subtract it next time, you get a z to a power, etc. Okay, folks, what is that? It's a power series. How do you sum a power series? First term minus first missing term over 1 minus the common term. First term is z. The first missing term is z to the r plus 1 over the common term 1 minus z. Now I want to denote the zeros of this baby as follows. I want to give them some notation. So we're going to denote the R zeros that we're looking for of this bracket in the equation above as, I'm going to call them z sub 1, z sub 2, out through z sub r. There are of them. And we got to find them. As I've told you many times before, that's the only part of solving these difference equations. Finding the roots of a polynomial. Okay? So we can write the denominator as follows. In terms of those roots, it's the following. First of all, let's take the r mu outside. So I get an r mu, and I got a 1 minus z, I know that. And these other guys all involve a z minus a z1, a z2, etc. And that's going to be the following. 1 minus z over z1 times 1 minus z over z2 out through 1 minus z over zr. Whatever they are, I can write it this way. Having done that, then I can say that P of z, which we have at the top of this page, is what I just wrote for the denominator. Let's put the numerator in now. Okay, so we're going to get the following expression. We're going to get our friend. Well, look, I've got an r mu 1 minus z right here. And son of a gun, there it is in the numerator. Here with this. So cancel them immediately. Let's get rid of them right now. Okay? So when I write this out, all I'm left is a 1 minus rho upstairs. And downstairs, I got these factors, 1 minus z over z1, etc. Now it turns out that these R roots are unique. There's no multiple roots. We're not showing that, but it's the case. So now, John, we can do the partial fraction expansion, okay? We know that P of z, this thing I just wrote down with this denominator, is equal to a product of a bunch of roots. Well, let me do it this way. Let me write it more simply. Let me put the 1 minus rho in there so I don't lose that. And then we're going to get a bunch of these roots, summation, how many I equals 1 to r, that's how many roots there are, of some numerator, a sub I, yet to be found, over these roots, 1 minus z over zi. That's exactly what we mean by the partial fraction expansion. Where ai, we know, is the product for j from 1 to r, except you're going to skip it when j equals I. So j not equal to I. Remember, when you take that root, you divide it out and multiply the rest of what's left, which is 1 over 1 minus zi over zj. Namely, you replace the z by the factor you've pulled out, the zi factor. Okay? Now, what we have here is we're going to end up with terms like we've seen so many times, a over 1 minus some number alpha z, whose z transform back in time domain is a alpha to the n, that you remember. So the final result is that capital P sub j is equal to our friend 1 minus rho times the sum. And when I invert each of these, I get a function to a power. I'm going to use the jth power here. This is the summation now from j equals 1 to r of these ai's, which I've calculated, times z sub I to the minus j. J equals 1, 2, etc. And P0, we know, is 1 minus rho from before. That's the answer. What's the hard part? Finding those roots. This is the solution to MER1. And notice what it is. It's a weighted sum of geometrics. Which is somehow pleasing. It's pleasing because geometrics are the memoryless discrete time distribution, and this came out of exponentials, which is a continuous time memoryless. But that's a solution. Hard part, find the zi's. Now, we're not finding the mean waiting time here. We'll do that later. We're going to stick with this for now. Okay. What's the next thing you think I'm going to do? What's the next natural thing to do? I just did MER1. What's next? Flip it. ERM1. A slightly different approach, but the same idea. So we're going to basically assume that A of t, the inter-arrival time, is an Erlangian distribution. And in particular, we're going to write it this way as an Erlangian. It's R lambda times the quantity R lambda t to the R minus 1 e to the minus R lambda t. All of that over R minus 1 factorial. That's the Erlangen distribution, but I'm applying it to the inter-arrival time. So before anybody comes in, well, they come in by that density, okay? So let's draw the picture. We have a queue. We have a server. Customers come in. They join the queue. They join the server. They leave. And the service time is now pure exponential. That's what this m means here, at a rate mu. But they're coming in as an E sub r density. Now, what's the state variable for this? The inter-arrival time is not memoryless. So I need to know how long it's been since the last arrival. That affects when the next arrival comes in. So I can track that and track how many people are in the system. It's two-dimensional, son of a gun. So you tell me what to do. Okay, okay, don't answer then. Thank you. Someone else have an idea? Same idea as before, but a little twist on it. Every customer that comes in has gone through R stages of service. If I told you before somebody comes in, they've passed through J stages of arrival, then you know they got R minus J left to go, plus 1. So you know the distribution of time to go. So knowing how many stages the arrival has already passed through before he comes in is all I need to know. So the state variable is going to be the following. Will be equal to the number of stages of arrival in the system. Now let me explain what that means. If you look at somebody who's already arrived, say right here, how many stages of arrival did that individual pass through? He's arrived, so how many stages of arrival did he pass? See, what's happening back here, there were all these arrival stages. And when they pop out of here, then you arrive. How many stages of arrival did somebody who's already arrived pass through? R. So I'm going to say every arrival that's in the system sort of counts for R stages of arrival he passed through. So if you tell me how many customers are in the system, multiply that by R, that's how many stages of arrival in the system. If I gave you that number, you know how many people are in the system. But if I also told you how many stages of arrival the arriving customers passed through, that tells me exactly how long it's going to take them to arrive from a distribution point of view. So as many stages as a customer has passed through on his way in, up here, tell me that number. He's passed through 3, and everybody here has passed through R. That's the state variable I want. Okay. So that's equivalent to how many customers are in the system and how many stages of arrival the arrival customers pass through. That's what I needed to know to get rid of the memoryless, to get rid of the memory property. So let me draw the picture a little more carefully now. Let me redraw this again. Here I'm going to draw my arrival box. 1, 2, I, R. There's a whole bunch of arrival boxes here. I'll do a red circle around the whole thing. This is the arriving box. Finally, that customer arrives. This is a rate mu. And this is still going to be a rate lambda coming in, because that's the way I cooked up this A of t. The arrival rate here is lambda. Now, suppose I told you I wanted to calculate how many customers, how many stages of arrival I have. So for every customer, suppose there were k customers in the system. That means there are k minus 1 here and 1 here. How many stages of arrival are in the system right now? Every one of these guys went through R stages. So did this guy go through R stages. And then there's somebody in the ith box right here. How many stages did he go through? How many stages of arrival has he already finished? I minus 1. So all the red stuff added up, and you get the number of stages. So I'm going to claim, let's just finish this now. P sub j is going to be essentially the number of stages of arrival in the system, including the one that's coming in. And if I tell you there are k in the system, k customers in the system, let me be clear about that. And the arriving customer is in stage I of arrival, then J is equal to what? Is equal to RK, R for every customer in the system, plus I minus 1 the guy is arriving. And that's the state variable I'm going to track down. If I get that and solve it, I can tell you how many people are in the system, etc. Now, we have to quit right now, but give me a clue what's the next thing I'm going to do. What's your name again? Mike? Nick. What's the next thing I do? I'm picking on you because you gave me the answer earlier for the other system. Yes. And once I got that, we play the Nick game. Start drawing circles. He likes to draw circles in the sand. Okay. So we're going to do that. And we'll pick that up on Wednesday.